So in part A of the problem, we're asked to find the rate at which the radial vector sweeps out area for a planet orbiting the Sun. Now, let's start off by determining the area swept by the radial vector as it moves from theta to theta plus d theta in the orbit of the planet. So here we've drawn a diagram of the area swept dA by the radial vector for an angle, small angle d theta. Now we can approximate the area as a triangle whose base is r and whose height is r d theta, which is given by the arc length formula. So we have that the area dA swept by the radial vector is equal to, well, the area for a triangle is half times the base, which is r, times the height, which is r d theta. So that is just half r squared d theta. Now, the angular momentum of the planet is given by its moment of inertia times its angular velocity, omega. Now, if we treat the planet as a point mass, its angular momentum, or its moment of inertia, is just given by its mass, m, times its distance from the point of rotation, which is r. That is squared. And then that's multiplied by omega, which we can rewrite as d theta dt, which means that d theta dt is just equal to L over m r squared. Now if we plug that back in, or before we plug that back in, let's take the time derivative of the area dA. So then the rate of change with respect to time of the area swept by the radial vector is equal to the derivative of the right-hand side. Now, the radius, we're going to assume, does not change much with time, so that's a constant. So that's just half r squared. And then theta changes with time, so we get d theta dt. And if we plug in for d theta dt, we get half r squared times L over m times r squared. Now the r squareds cancel, and we get our final answer, which is L over 2m. So that's our final answer for part A, for the rate of change of the area swept by the radial vector. Now in part B, we are asked to derive Kepler's third law from Kepler's second law and the equations that we were given. So here we've drawn a diagram of the orbit of the planet. So B is a semi-minor axis, A is a semi-major axis, and this point here is one of the focal points of the ellipse, which is a distance f from the center. Now, we know that epsilon is the ratio of the distance of the focal point from the center over the length of the semi-major axis, which is A, which means that F is just equal to epsilon A. Now, we also know that for any point on the ellipse, the sum of the distances from that point to the two focal points is equal to the length of the major axis, or twice the length of the semi-major axis. Now, by symmetry of this point, we know that the distance from this point to each focal point is the same, which means that this distance here, d, is equal to the length of the semi-major axis, which is a. So we also have d is equal to a. So by Pythagoras' theorem, we have that b squared is equal to d squared minus f squared. And if we plug in for our values for d and f, we get a squared minus a squared epsilon squared, which is also equal to a squared times 1 minus epsilon squared. And that implies that b is equal to a times the square root of 1 minus epsilon squared. Alright? Now, the period, by Kepler's second law, we know that the rate at which the radial vector sweeps out the area is constant, which means that the period is just given by the total area of the ellipse divided by the constant rate at which the area is being swept, which is given by dA dt. So for an ellipse, the area is just pi times a times b, where a is the semi-major axis and b is the semi-minor axis. And that's all divided by, well, we can plug in for our expression that we found in part A for dA dt. So that's L over 2m. So that just simplifies to 2m pi ab over L. Now we can plug in our values for b and L, which we were given in the problem statement. So the period is equal to 2m times pi times a times, well, here we have an a squared times 1 minus, sorry, not a squared, a times the square root of 1 minus epsilon squared. That's all over the square root of g times big M times little m squared, which we're just going to take out and pull it out and put an m here, times a times 1 minus epsilon squared. Now, the little m cancels, and the a's group up, and if we factor out the square root of gma, we get 2m pi a squared, square root of 1 minus epsilon squared, over m times the square root of big G times big M times the square root of a, which we'll write as a to the 1/2, times the square root of 1 minus epsilon squared. So now it's easy to cancel out terms from the numerator and the denominator, and we get that our period is just 2 times a to the 3 over 2 divided by the square root of g times big M. Now, this means that if we square the period, so t squared, we get that t squared, or we're going to write it over here, we get that t squared is equal to 4 times a to the 3rd over big G times big M. So here we've shown that the square of the period is proportional to the 3rd power of the length of the semi-major axis, which is Kepler's third law.